Welcome to the lecture 9 on this series of acoustic materials and metamaterials. In the previous class we were discussing about various ways of representing sound and measuring sound. So we studied about spectrum analysis and how the sound is represented as a distribution of acoustic intensities over a frequency scale, and that frequency scale is then divided into small bands for analysis, just to increase the computation time. Rather than having a continuous scale, we divide the frequency scale into small bands and we analyze the intensity over these individual bands to get the full spectrum. So in this class also we will continue our discussion on sound signal analysis. So here the outline for the course is, we will study about octave and 1/3 octave bands, and then we will study how do we combine the sound pressure levels for different sound waves. And then after that we will have a tutorial session where we will do some numerical problems for a better understanding. So as I said before, the spectrum analysis is done in noise control because human hearing is highly frequency dependent, and the knowledge of how the intensity is distributed over frequency is very important. And usually a spectrum is calculated by dividing the frequency scales into certain bands. So if we have a frequency scale like this, a continuous frequency scale, it is divided into bands. So it is cut into such bands, and then so each band is characterized by some upper frequency and some lower frequency, and the difference between this upper and lower frequency gives you the net width of the band, which is called as the bandwidth. So different bands are obtained, and then the intensity distribution can be studied over these fixed bands. So it's sort of like a histogram kind of a graph. So this increases the computation time, so we study it by digitizing the frequency scale. So two common types of bands exist. This is done to facilitate comparison between the manufacturers from all across the globe and from the measurements from different instruments. So ISO has specified that all across the globe we have some standard bands so that we can compare the data of one researcher with another researcher at any part of the world. So the two common bands which are used are octave band and 1/3 octave band. So octave band, here the bandwidth is wider, so this is a more wider kind of a band, something like this, and this is a more finer band, 1/3 octave band. So if we get suppose 4 bands in a particular frequency range, 1/3 will be, every band is again divided into 3 separate bands. So we get a more finer detail here. We will see that in the subsequent slides also. So this is a wider bands for quick analysis. This is a narrow band. Computation time can be slightly higher, but it will give you a more detailed frequency analysis. And each of this band, it is characterized by some upper frequency limit and lower frequency limit and the center frequency Fc. The bandwidth is simply the difference between the upper and the lower frequencies. And for octave band, the way the calculation is done is that we start from, for both bands we start from somewhere around 25 Hz or so, the lowest frequency, and then for an octave band the upper frequency is just the double of the lower frequency, and the center frequency then is the geometric mean of upper and lower. But for 1/3 octave band, the upper frequency is 2 to the power 1/3 times of lower frequency. So as you can see here, this is twice of this is 2 to the power 1/3 of this. So the width of this particular band will be more, because here upper frequency is more apart than lower frequency. So this table lists the bands. So this is just giving you the center frequency for a particular band. So we have a band from, let's say, 25 to 40 Hz. The geometric mean occurs somewhere around 31.5 Hz. So the center frequency, so every band has got two frequencies which are the limits, but the center of that is taken as the center frequency, and for easier notation we simply denote a band with its center frequency. So this is This is how the audible range is divided in an octave band. So these are the center frequencies of the octave band, and then 1/3 octave band, the same frequency range 0 to 16 kilohertz can be divided. Sorry, the audible frequency range is 20 hertz to 20 kilohertz. So 20 hertz to 20 kilohertz is divided into these bands for octave scale, and 1/3 octave band, it is so many. So as you can see here, the number of bands are limited, they are more wide, so number of bands obtained are limited. So the observation point is also limited, so we get a quick analysis, but it is not very detailed. This is a more finer band and it gives you a more detailed analysis. So to compare the two, let's say we have the same signal. This is how this signal comes out in octave band, and this is how the signal looks like in 1/3 octave band. So when you observe this in an octave band, you will see that okay, this is how the signal is varying. The intensity is lower here, then there is a peak around 1 and 2 kilohertz, and then it again decreases like this. So this is what observation you get from octave band. But when you do a more finer analysis, then you get certain dips and peaks which you missed out in the octave band analysis. So when you do a more finer detail, then you see that okay, although roughly this is the distribution pattern, but if you go for a more detailed analysis, what you see is that even at this point it is not continuously increasing, but there is a dip here, and then also again it is not continuously decreasing, but there is a peak here. So you had missed a dip and a peak which you now observe when you do a more detailed analysis. So now let's study that let's say we have 2-3 machines in a single room, and every machine is emitting some sound level. So one is emitting, let's say 60 dBs, other is emitting, let's say 40 dBs, 50 dBs, and so on. Then what will be the combined effect of these machines when they are working together? So this we need to know. So for that we are going to see how the SPLs they combine together. So if we have individual SPL sources, SPL1 plus SPL2 plus SPL3, so their combined effect will be what? So for that we need to know that there are two types of sounds. When two sounds they have the same frequency, same waveform and constant phase difference. So usually then they are called as coherent sounds. So coherent sounds are usually generated from the same source because frequency is highly dependent on the source. So suppose the same source is generating two signals at some phase difference, then they are coherent. So if two sounds are coherent, then the way sound pressure levels are combined will be different, and all the other sounds which do not have the same frequency and fixed phase difference and the same waveform, they become incoherent. So most of the common sounds encountered are incoherent in nature because they are signals coming from everywhere, some coming from a particular machinery, some coming from vibrating surface, some coming from a general human talking somewhere outside. So in general, any particular area is a combination of many sound waves, and these sound waves are in general incoherent in nature. It's very rarely that we find coherent sounds that are coming together. So the addition and subtraction depends upon the nature in which these sounds they interact. So we had already studied before when we were doing the standing waves. So what we studied was that suppose we have two different waves, then the resultant wave could be a standing wave. So the resultant wave is simply obtained by summing or subtracting in whatever case. So it is simply a vector summation of their acoustic pressures, and that is how we got a standing wave. When we had two waves traveling in opposite direction, the equivalent wave became a sum of the acoustic pressure of the two waves. So in that case, both the waves they had the same frequency component, they had the same omega and k. So they were coherent in nature. So that kind of addition and subtraction is only applicable to coherent sounds. So what happens when the coherent sounds or the sounds with the same frequency and waveform, they are simultaneously present in a medium, then the total acoustic pressure is a vector sum of the individual acoustic pressures, and that is what we had done in our previous class when we were doing standing waves. when we are solving the equations of standing wave. So, we are simply adding up the pressures together. And when we also studied about the sound propagation through medium boundaries. So, whenever we are deriving the conditions like the equation of continuity, so we used to simply add the pressure of incident and the reflected wave to get the total pressure at the left hand side of the boundary. Again, in that case also, both these waves, they had the same frequency. So, they were coherent, and that is why the summation of pressure was valid. But if the sound waves, they have different frequencies, they are incoherent in nature, then in that case, when such incoherent sounds are present simultaneously in a medium, then the pressure summation is not valid. What happens is that the total intensity due to these sounds is then a vector summation of their individual intensities. So, here the P effective is simply P1, not P1 plus minus P2 plus minus P3 and so on, and here the intensity is getting summed and so on. So, not the pressure but the intensities. So, let us study these cases one by one. Let us take the incoherent case first. So, suppose in a medium we have n different sounds, and each sound and the individual pressure of each sound is P1, P2, P3 and so on till Pn. So, we have n such different sounds and they are present together in the medium, and we have to find how the individual totals, what will be the equivalent sound pressure level in terms of their individual sound pressure levels. So, we know that the intensity is a summation of their individual intensity. So, what we do is intensity again, because all of them are together present in the same medium, and P is equal to P square by rho C. So, rho C is same, so I is directly proportional to P square. So, we can represent the summation of intensity as the summation of their square of RMS pressures. So, P effective, the net effective RMS pressure square will be P1 square plus minus P2 square plus minus P3 square plus minus Pn square and so on. So, here I have used plus and minus both, because so that this equation is valid both for the summation of sound as well as subtraction. So, you can use it for both cases, to add the sounds or to subtract the sounds. So, usually you square it, the squares they follow this rule. Now, if we divide both these sides by P reference square, dividing them by P reference square, this is what you get. And if you do 10 log 10 of this on both the sides, so this is the value you get. Now, this is what, by definition, this becomes the sound pressure level of the effective wavefront. So, this is the effective sound pressure level. When all these individual sound waves, they are present together, then the total sound pressure level is given by this form. So, this is the total sound pressure level, which is given by this expression 10 log 10. We have separated these. So, we have got 10 log 10, this plus this plus this plus this and so on. So, now let us derive, let us see how these expressions calculate these expressions in terms of their respective SPLs. If you calculate these expressions in terms of the SPLs, so let us say the SPL of the nth sound, the formula for that will be 10 log 10 Pn square by P reference square. So, if you solve this equation, then ln by 10 becomes log 10 of Pn by P reference square, and then you do a 10 to the power on both ends. So, this log cancels out, and what you get is 10 to the power ln by 10 is equal to Pn square by P reference square. So, you are able to obtain the value of this expression in terms of the level of the sound. So, again putting these respective values, what you get is the total effective SPL for, suppose we have sounds that are emitting SPL 1, 2. So, suppose we have n sources with L1, L2, L3 and so on, such individual n sources having individual levels in decibels. So, these are all in decibels. Then the total decibel, the total decibel level when all these sounds are present together will be the total decibels when all these sounds are present together will be given by this expression. So this is how the SPL combines. So it's a complicated expression, but you need to remember it. So this is where the sounds are incoherent in nature. But what if they are coherent, they are coming from the same source? Then we know that P is simply a vector summation of P1 plus minus P2, whatever. So suppose say we have one pressure is given as this particular vector P1 and the other pressure has some phase difference phi and is P2. So we can simply use the vector summation equation. We know that the vector summation for two different vectors is going to be mod of one vector square plus 2 second vector square plus 2p1 p2 times cos whatever is the angle between the two, del phi. And similarly, if it is subtraction, then a negative will come only in this term. So we are using this vector summation equation here, where this is the phase difference. So what is phase difference? Suppose one P1 is a e to the power j omega t minus kx, it is a forward propagating wave. The other P2 is some a e to the power, so this is a e to the power j omega t minus kx plus some angle. So it is having the same waveform, only that the starting point is now different. So there is some phase difference. So this is what we have taken into account. We divide both the sides by P reference square, sorry. So P reference square we divided by, so this is the expression we get. Taking 10 log 10, this is the expression we get. So SPL effective, this 10 log 10 is SPL effective. It becomes 10 log 10 of P1 by P reference whole square plus P2 by P reference whole square plus minus twice of P1 by P reference into P2 by P reference into this. So let us find these individual terms in terms of their corresponding SPL. So just like we did in the previous case, the L1 of the sound will be this. So L1 by 10 will becomes this quantity. If you take 10 to the power on both the ends, so this comes out to be 10 to the power L1 by 10. Similarly, P2 square by P reference square will be 10 to the power L2 by 10. So we have found these values in terms of their levels. Let us find the value for this. Now if we take 20 log 10 of this particular expression, then this can be written as, by the property of log, it can be written as 20 log 10 of P1 by P reference plus 20 log 10 of P2 by P reference. And this is what? This is level of 1, this is the level of sound 2. So L1 plus L2. So this is coming out to be L1 plus L2. So which means that this log thing, this thing will be L1 plus L2 by 20, solving this equation. So once this into this is log 20, you take 10 to the power on both the sides. So you get this expression as 10 to the power L1 plus L2 by 20. So this was the expression for the total SPL when two different coherent sounds are present together. When we put these values in terms of their respective levels, so this is what we get. So here suppose we have two different sound sources which have level L1 and L2, some decibels. Let's say one has 40, one has 50 decibels. Then their total, then when they are present together, the total decibel is given by this formula. You put this formula here and you get the total decibels for coherent sounds. So you've got these two formula here, this one and this one. This is the most commonly used one because most of the sounds, they are incoherent in nature. Now let us start with solving some problems. So the first problem here is the sound level from one speaker is 60 dB at 1 meter and two such speakers are purchased and placed side by side in an open field. What is the total sound level at 2 meters? So if the nature of the waves is not given, it's not given whether it is coherent or incoherent, then we see that okay, these are two different speakers placed together, so we assume it is incoherent in nature. Assumption that incoherent sounds. Now let us see. Now we know that Also, when the type of wavefront is not given to you and it is only said that there are two speakers. So, in general, in real life, whenever there is no constraint in the medium, we have open field or a large space, and we have two sources which are small, whose dimensions are relatively small compared to the dimension of the space. Then we assume that they can be assumed as point sources. So, the speakers can be assumed as point sources. So, these point sources will have spherical wavefront. So, whenever the dimension of the source is much smaller compared to the dimension of the medium. So, when source dimension much smaller than the dimension of the medium. So, if a small speaker is present in a large room, then it can be assumed, then source can be assumed as point source. So, wavefront will be, therefore, wavefront will be spherical. So, this is the assumptions which we have to take whenever solving such problems. So, now we have these two assumptions. Let us solve the problem. Okay, so these values are given to us. So, because it is a spherical wavefront, so which means that the pressure will be inversely proportional to the distance of measurement. So, pressure is inversely proportional to the distance of measurement, and it is given that the pressure coming from the pressure coming from one microphone at 1 meter's distance is 60 dB. This is given to us. Then this means that 20 log of the pressure at 1 meter by P reference, this comes out to be 60 dB. Then the pressure at 2 meters will be what? The pressure at 2 meters will be 20 log of P at 2 meters by P reference. This will be the total pressure at 2 meters. And we know that this is the pressure wavefront. So, pressure at 1 meters is inversely proportional to 1 by R. So, pressure at 2 meters by pressure at 1 meter will be what? It will be 1 by 2. It is inversely proportional to R. So, now the distance has been doubled from 1 meter to 2 meter. So, the pressure is going to reduce by half. So, this comes out to be 20 log P of 2 meters by P reference. So, P of 2 meters is now converted into P of 1 meters into 1 by 2 using this relationship. So, what we get is this becomes 20 log P at 1 meters by P reference minus 20 log of 2 decibels. And this value we already know. What is the pressure value? What is the SPL at 1 meters? It is 60 dB. So, this is 60 dB minus 20 log 2, which is going to be 6 dB. So, this comes out to be 54 dB. So, this is the SPL by one speaker at 2 meters is coming out to be 54 dB. So, here an important observation is that whenever distance of sound measurement is doubled, then the SPL decreases by 6 dB. So, if the distance is double, that does not mean that then the pressure will reduce by half. So, the pressure is reduced, or you can say when P is reduced by half, SPL decreases by 6 dB. So this is a more correct way of saying this. So this is first observation. So whenever the acoustic pressure reduces by half, then the SPL over here it decreases by 6 dB. SPL does not reduce by half, it reduces by 6 dB. So we have obtained this. Then the equivalent pressure at 2 meters is what we have to find, and this will be using the formula 10 log 10 of 10 to the power the equivalent, the level at 2 meters for one microphone, which is 54 by 10 plus 10 to the power. The second loudspeaker is also making the same noise, so it is 54 by 10. So 2 sounds. So now we have 2 speakers placed side to side, then their total SPL at 2 meters will be 10 log 10 of SPL due to 1 divided by 10 plus 10 to the power. So we have used this formula of combining the incoherent sound sources. We have used this formula. So this formula we have used. So what you get is, it is simply 10 log of 10 to the power 54 by 10 multiplied by 2, which we take out, which becomes 10 log of 2. So this 10 to the power log, this cancels out. So what we get is, this is 54 decibels plus 10 log 2 is going to be 3 decibels. So the total decibel we are getting is 54 decibels, and that is going to be our answer. So the answer is, the total sound is 54 decibels. Another observation that we get is that if 2 equal SPLs are present simultaneously, so 2 sound sources, when they have the same SPL, then their combined effect is SPL increases by 3 dB. So as you can see, that the decibel scale, it compresses all this difference. So here we have let's say we have 2 sound sources, one is emitting 60 dB sound, the other is emitting 60 dB sound. Then the combined effect is not going to be 120 dB, it is going to be 63 dB. So it increases by 3 dBs. Let's solve one last problem for this class. So this is a recall problem from what we studied in standing waves lecture. So here we have to find the fundamental frequency of a long tube with one end closed, one end open, and 1 meter length containing air at room temperature. So we already know how to find fundamental frequency of a long tube which is closed at both the ends. Now here we have a long tube which is closed at one end, open at one end. So here the trick here is that the acoustic pressure is 0 at open end. So what we mean here is that, suppose this is a long tube, one end is rigid, this is also rigid, and this end is open. So what happens at this end is that whatever velocity is entering here is just going out. So this end is just like an open window. So here it is offering no resistance to the flow of sound waves. So which means that the impedance is going to be 0 at this end. So let's say at x equals to 0 we have a closed end, and this is at x equals to L. So this is at x equals to L. At the other end we have a open end. So at the open end it offers no resistance to the flow of sound. So the Z becomes equals to 0. The impedance is 0. There is no resistance, which means P by V is 0, which means P is equal to 0. So the acoustic pressure here becomes 0. So this is the condition we use for x equals to L. P is 0 at x equals to L, and minus del P by del x is going to be 0 at x equals to 0. Why? Because V is 0. So at the rigid end it offers full resistance to the flow of air. So no particle can go beyond that. So particle velocity becomes 0 at region end and the pressure becomes 0 at the open end. So these are the two conditions. So let's solve using these conditions. So we assume a general form of pressure A e to the power j omega t minus kx. So it is a composition of a forward and the backward propagating wave. So applying the first condition, dp by dx at x equals to 0. So this will be, so let us calculate what is dp by dx. It is going to be minus a k j times e to the power j omega t minus kx plus b k j e to the power j omega t plus kx. So putting this at x equals to 0, what will be the value? This cancels out, this is the common term. Overall what we get is minus a plus b is equal to 0 when you solve it. So b is equal to a is what you get. Putting the second condition, that is p is equal to, p at x is equal to L is equal to 0. So this was the first condition. So from the first condition we got this value. The second condition is that the acoustic pressure becomes 0 at the open end. So putting that here, what you get is, now b is equal to a. So which means a e to the power minus j k L plus e to the power plus j k L. Here e to the power j omega t is a common term which we have removed. This becomes equals to 0. So when you put this and using the Euler's relation, what we get is cos kl minus j sin kl plus cos kl plus j sin kl. This entire thing will be 0. So this cancels out. So what overall we get is that cos kl has to be 0 because a is non-zero. This implies that when will be the cos function 0? At the odd multiples of pi by 2. So this is going to be the condition. N starts from 0, 1, 2, 3 and so on. So at n equals to 0 we have pi by 2 as the first solution and then we continue. So this is what we get. Then we have to find out the frequency, I think. We have to find the fundamental frequency. So let's derive what is the equation of frequency. So this means that k is equal to 2n plus 1 times pi by 2, 2 pi f by c is equal to this quantity. So f is what? The natural frequency is given by 2n plus 1 times 4L into C, 2n plus 1 C by 4L, where n is 0, 1, 2 and so on. And we have to find the fundamental frequency. So F naught or the lowest frequency will be when you put n equals to 0 in this equation. What you will get is, it will be C, which we take as 340 for air at room temperature, into 4 into 1 meters, which is the length of tube. So it comes out to be approximately 85 Hertz. So this is the solution. Here I have noted it down. So the natural frequencies for open closed tube is given by this, and the first mode is when we put n equals to 0. So this is the first mode. So anyways, thank you for listening to this lecture.